In the last lecture, we introduced the broadcast channel. In the broadcast channel, there are three sources, one encoder, and two decoders and sinks. The source put out statistical independent messages W0, W1, and W2. So there are, of course, n times R0, n times R1, and n R2 bits. That means we have messages, index message sets from 1 to 2 to the n R0, 2 to the n R1, and 2 to the n R2. So the message W0 is for both things, and it's called the common message. The messages W1 and W2 are for thing 1 and thing 2. That means W1 is for thing 1 and W2 is for thing 2. We call them dedicated messages. And the goal is of decoder 1 to give an estimate of W0 and an estimate of W1. The goal of decoder 2 is to give an estimate of W0, that's the second estimate of the common message, and an estimate of the dedicated message W2. So the encoder maps W0, W1, and W2 to a sequence x to the n, and the channel, which goes from x to y1 and y2, puts out two sequences, y1 to the n and y2 to the n. And now, as I told you already, decoder 1 uses y1 to the n to compute its estimate for the common message and for its dedicated message. The same is done by decoder 2, who receives W2 to the n and gives an estimate of the common message and an estimate of its dedicated message. Now our goal is to find rate tuples R0, R1, R2, for which we can make the error probability arbitrarily small. This error probability is that the first estimate of the common message, the second estimate of the common message, the estimate of the first dedicated message, the estimate of the second dedicated message is not equal to the real common message, the first dedicated message, and the second dedicated message. And the closure of the region of achievable tuples R0, R1, R2 is the broadcast capacity region CBC. As I told you already last lecture, this region is not known in generally. We just know upper and lower bounds. Therefore, we first will look at special cases where one knows the exact region. First, we did some preliminaries. So what we saw is that if we know that we have a tuple R0, R1, and R2, which is achievable, then we know alpha 0, R0, R1 plus alpha 1, R0, R2 plus alpha 2, R0 is also achievable if all alpha I is greater or equal 0 and the sum over all alphas is equal 1. The idea was more or less that we use the parts of the common message for the dedicated message of decoder 1 or decoder 2. The next property is that the capacity region depends only on its marginals, y1, x under the condition x, and y2 under the condition x. These are the marginal channels from x to y1 and x to y2. And we saw that the proof was not so difficult, and we really saw if we have the same marginals, then it's the channel has the same capacity region. The next thing is about channel coding binning. So we prove, if we look at the probability, then the probability that an error occurred is small if R1 prime plus R2 prime is greater than the mutual information between X and Y. The idea is really that we have to choose the bins big enough, so that that the error is small enough. The fourth property is really one property which belongs to our first section. It's somehow about typical sequences. So we assume that xi is emitted by a discrete memberless source, px under the condition u, and un is typical concerning the joint distribution of u and y. And then we could show that then the probability that xn is typical concerning the joint distribution about of u, x, and y under the condition that un is equal un is approximately 2 to the n times the mutual information between x and y under the condition u. We just need our previously result to prove this. Also in the normal way. It was also not such a difficult proof. Then we start to look at special cases. The first special case we looked at was the COM message capacity. In this case, we only have one message, which is sent to the encoder, and decoder 1 and decoder 2 have the goal to give an estimate of this message. Thus, we only have a common message. We don't have any dedicated message. And we see that this is very similar to our construction for the discrete memberless channel, where we have, in principle, only one decoder, not two decoders. So the idea is we generate 2 to the nr0 code words by choosing n times 2 to the nr0 symbols independently using a distribution px. So we just do random coding as we did for the discrete memberless channel. And then we use this randomly designed codebook as follows. The encoder gets a message W0, and then you look at his codebook and transmit xn of W0. So decoder 1 receives now y1 to the n, and he tries to find a W0 tilde such that xn of W0 tilde and y1 to n is jointly typical concerning x and y1. And again, we have to do this in the following way, that we have a function, and if there's more than such index, we have to choose one. We always choose the first in the list. We can think about this. And if we don't find something, then it's an error. We just put out then the message one. And the same is done by decoder 2. We just change all ones here, y1 to the n to y2 to the n, and then we proceed in the same way. As a result, we get that the rate we can assume is the maximum over all px, distribution px, and the minimum of the mutual information between x and y1 and the mutual information between x and y2. Somehow that's something what one can assume. Because if we have only one decoder with this marginal channel x and y1, and we don't care about the second decoder, then the first decoder assumes this rate here, and the second decoder assumes also some rate, but of course perhaps the maximization, it's not the correct distribution chosen here. So that's the reason why we have to take here the maximum and the minimum. And the converse is also very similar to the discrete memberless channel. We use Fano and concavity of the mutual information. Now, last semester, I remember there was a big discussion if max-min is the same than min-max. And here's the proof. Max-min of some function is always less or equal than min-max of some function. Because if you look at, you all will agree if you take the minimum of all epsilon, f and xy, then this is lesser equal than f of x and y. Now, of course, we can take the maximum over x on both sides. Still, the same inequality holds. Now we take the minimum over y on both sides. So then we have the minimum of y, maximum of x, minimum of y, fxy is lesser equal to the minimum of y, maximum of fxy. Now, since the maximum of x and the minimum of y is independent of y, we can write instead of min, max, min fx and y, just max x and min y of fx of y. And then, of course, we have that we want. I think you can also make it clear by example that this could be bigger equal than this. Then we look at the next special case. This is a dedicated message capacity. The idea is now we do it the other way around. We have no common message. We only have two dedicated messages. So we consider a distribution PU1, U2, sorry, and let U1 and U2 be the respective alphabets of U1 and U2. And we consider functions that map symbols in U1 and times U2 to symbols in X. And we write then X equal F U1 and U2. And so Xn is equal Fn of U1n and U2n to mean that Xi is f on U1i and U2i for I equal 1 to n. So it's a general way we already did it. So we use a bigger alphabet instead of directly create a random code book on the normal alphabet we use. We just use the alphabets U1 and U2 and create the code books. So we do it somehow like for Slepian Wolf. So here it's in more details. We generate, so we use binning also. We generate 2 to the n R1 plus R1 prime. That's the size of the bin here again. Code words U1n, W1, V1, where W1 goes from 1 to 2 to the n R1. That's the rate for the first dedicated message. And V1 goes from 1 to 2 to the n R1 prime. This somehow is the size of the bin. So by choosing the symbol U1i, W1, V1 independently using PU1. So it's a random generated code. So similar, we generate 2 to the n R2 plus R2 prime code words for the second dedicated message. So we have U2 to the n of W2 and V2. W2 goes from 1 to 2 to the n R2, where this is the rate of the second dedicated message, and V2 goes from 1 to 2 to the n R2 prime, where this is the size of the bin again. Now, the encoder, he gets the dedicated message W1 and the dedicated message W2 for the first and for the second receiver. So now he tries to find a pair V1 and V2 such that U1 and U2 in the codebook, so it depends of W1 and V1 tilde and W2 and V2 tilde, is jointly typical concerning U1 and U2. So he looked in his two random created codebooks and tried to find two code words in such a way that they are jointly typical. If there's one or more, then choose one. Again, we choose the first in the list, and we transmit. We use our function now and transmit xn, which is a function of U1 and U2. So in practice, the decoder might know ahead of time which V1 and V2 is chosen. That's the comment we already gave last time. However, this is not necessary since the receiver will discard this index as shown in the next step. Okay, what do the decoder do? So the decoder 1 receive Y1 to the n, and he tries to find a pair W1 tilde and V1 tilde such that U1 to the n in his code books, depending on W_1 and V1 tilde, and Y1 to the n is jointly typical concerning the joint distribution of U1 and Y1. If there is one or more such ones, then choose the one and put also corresponding W1 tilde as W1 hat. And if there's no one, then we have an error and we just put out W1 hat is equal 1. Of course, decoder 2 can proceed as decoder 1, except here we have to replace index 1 as 2 everywhere. And as a result, we get, when we analyze this, we get the following rate pairs. R1, R2 is equal the mutual information between U1 and Y2 minus alpha times U time and U2, and the mutual information between U2 and Y2 minus 1 minus alpha, the mutual information between U1 and U2, where alpha is between 0 and 1. This is the rate region, and it's also optimal if you have only dedicated messages. So next, we start the lecture, the next topic, by looking again at this rate region.